Starting on, you will see how it goes out. All right, so this needs to be visible in order to see the full story. So within a few seconds, we see how it goes out today. And I'm a bit worried that is too loud for you. Or is it so that is louder than is more understandable? Sure, makes sense. So let's put the volume as much as we can. All right, so while YouTube officer is checking how it appears, let me explain you something. Remember last week I mentioned that from this on it's just downhill. It's going to be pleasant life with no difficulties. That wasn't true. So I was just trying to attempt you to come here this Monday, and the reality is not as pleasant. Because, I mentioned that we're now in the top of the mountain and we're just coming down. No, that wasn't the case. So we still have another mountain that we have to climb. And another mountain is related to how to express the equation of motion with help of Lagrange multipliers. Maybe this is something that you're already familiar with. But now what we need to do is that we have to look at this in multi-body perspective. And that story is honestly a little bit painful story. It is the most deep mathematics so far. It is quite involving mathematics, but end of the story is beautiful. It's really, really beautiful. So my advice to you again is this. Don't get confused about the mathematical details. And the reward is coming soon. So today we're able to wrap up the whole story about how to express the equation of motion using a multi-body approach. And that will be something that gives you a tool that you can solve that, or you can express the equation of motion for any kind of mechanical system you want. Of course, the limitation we have in the beginning is that we are dealing the planar systems in this course. Oh, and you did not mention that the projection is not on. So what happened to projection? Was it on already or? No, not at all. So the power is on. Now it's on. Okay, is this big enough? So lights need to be tuned a bit. How is this? Oh no, a little bit too dark. This is all right, I think. This is perfect. Okay. Now, so it's week number 6. And today we are able to express our equation of motion by using the method where we are adding the constraints to original equation of motion. There are, roughly speaking, 2 different ways to account the constraints. We can either substitute the constraint to original equation of motion, or we can add the constraint to equation of motion with help of Lagrange multipliers. That's what we're going to learn today. All right, but prior to that, also I would like you to be aware that I'm here on next Monday too, and I recommend you to be here as well. And why is that? Because Monday after that, the midterm exam will be on, and I'm providing you information and hints, some hands-on advices like what it makes sense, what is the most optimal way you to prepare yourself to written exam. So be here. We can look the full story from the beginning to all the way to end of the equation of motion, all that together. And if you have any doubts, any comments, anything that is unclear, please familiarize yourself to this subject matter prior to next Monday, and we can discuss, like we always discuss. I don't think we discuss, but that's all right because I have my slides, so I can speak and you can listen, and then we can communicate on our own way, right? So now let's first summarize what we discussed last Monday. And after summary, we're going to look at the final thing, the final missing component that we need in order to express the equation of motion, and that is quadratic velocity vector. It is, with no thinking, it is something that we need because of the kinematics we use. I'm still going to provide you the physical interpretation related to quadratic velocity vector, and once we're done with that, then we're going to start look at how we can combine different bodies together, and more importantly, how is that we can express the equation of motion. Remember, the last week we started from this very same figure. There was a minor difference last week. Last week, the force that it is, let me see how is my writing today. Oh, it seems to be no writing at all. So let me see what's going on here. What is it I should select here to make my drawings? Pen or? I don't know. Drawings? Here, yeah. I see. Okay, so it's just that it seems that my pen is out of the battery, so I need to recharge this a bit, and then I can use it. Okay, so anyways, I was explaining this. Last week, this was the externally applied force. Week before that, not last week, but yeah, last week we summarized the force that was externally applied force. Then the last week we look, what is that we can do for inertia forces? And inertia forces can be treated exactly same way that the externally applied forces. No difference whatsoever. And again, look what is our objective here. We would like to express inertia forces in terms of generalized coordinates. And how they're expressed here is not, how they express in this equation is not with respect to generalized coordinates. How can I tell you that? Simply because if you look at the vector that I have in this expression, the vector that I have here is this one. So it's not, it's drawing, still drawing to me. This vector r dot dot, that is an acceleration with respect to generalized global coordinate axis x and y. So that particular vector consists of two components that are the acceleration component with respect to global x coordinate axis and acceleration with respect to global y coordinate axis. That's not good. I'm not comfortable with that because, again, I would like to express all the forces in terms of generalized coordinates. So how can I make that mapping to be possible? Well, that mapping, that can be carried out, again, with help of the concept of virtual work. Really the fundamental component that I need there is virtual displacement. And it may sound like, seriously, do we need it? Yes, we do. Because we have to find the relation between these two sets of coordinates, global and generalized coordinates. And that relation can be found out when we look at how the virtual displacement, the vector r, can be expressed. Remember, the vector r is a function of generalized coordinates, and that's why it is possible to express it like shown here. Partial r, partial q. I'm using my handwriting, so that's why it is a bit unclear. But anyways, hold on. Is it still all right? The voice is all right? Loud enough? Okay, good. So, what is that I'm after here? Why is that I'm doing this painful looking mathematics? I'm doing it because I really wanted to find the relation between global and generalized coordinates. And what is that relation? That relation is expressed by this partial r, partial q, which is a mapping matrix for us. Mapping two sets of coordinates, and that's exactly what we need. All right? So the big picture, that's clear for you. So it's like making me feeling very good. So you're all doing like this. So it's all clear. So what if I ask, what is a role of this matrix? Do you know what that role is? Mapping. So can I ask that as in-class quiz? You sure? You absolutely sure about this? That's good, so then I don't need to ask. Okay, so then let's look at the details. So how this actually goes. So, so now we have this inertia forces that are expressed like mass multiplied by acceleration. And now I wanted to be more sophisticated than just saying the mass multiplied by acceleration. So the way that I'm telling my mass is a volume integral over the density of the body within the boundaries of the body. So that's, more sophisticated way than just saying that the mass. Why this? Because again, remember, what makes a body? Body consists of a finite number of particles. Each one of these particles have their density. That's what I would like to collect. I wanted to collect this infinite number of particles. How do I do that in mathematically? Well, of course, with help of integral procedure. So that's how it happens. Now, in the case of virtual work done by inertia forces, I'm simply looking at how is this delta R, how that can be expressed. And that can be expressed like I just explained. And our miracle mapping matrix is the one that is under or inside of the circle here. Okay, then what followed was very, very painful mathematics. I'm sure you have no recollection what happened, but that's all right because we don't need to look at the details. What's enough is to understand what was the final outcome of all that painful mathematics. All right? So we substituted the expression of acceleration, which can be written in like shown here. And this was a little different than we looked previously because I wanted to express the acceleration with help of tenorized coordinates, the acceleration and the velocities. And then I'm using the mapping matrix, which in two-dimensional case can be written like it is shown here. So this one here is an identity matrix. This is a rotation matrix that is differentiated with respect to angle theta, and the vector u bar is vector u bar. All right? So once substituting all that mathematics to this expression, the tenorized inertia forces can be expressed such the way that it consists of two components. First one, I have here mass multiplied by acceleration. Mass matrix multiplied by acceleration of tenorized coordinates. And now suddenly all this makes sense because, now I can express my equation of motion such the way that my tenorized coordinates can be my vector of unknowns. Because this is what I really wanted to solve. This is what I would like to solve, and this is the way that I would like to express my equation of motion. Then I have this other component, which is can be considered as a force vector, which is quadratically related to velocities. Where that appears? Well, it appears from the fact that I'm using my body reference coordinate system, and my body reference coordinate system can be located anywhere I want. It can be located in the center of the mass. And now listen to me, because this is what I'm going to ask in my first in-class quiz. So you have your full attention to me. You have it? All right. If your body reference coordinate system is located in the center of the mass, that is a special case that gives you diagonal representation of mass matrix. So if your body reference coordinate system is located in the center of the mass, then you end up to have a diagonal representation of mass matrix. If your body reference coordinate system is located in the center of the mass, you will end up to have a diagonal representation of mass matrix. One more time. No, this is enough. Okay, so that's enough. That comes with another consequences as well. If that's the case, then your quadratic velocity vector will be equal to 0. So it will disappear. But in multi-body system dynamics, you can place your body reference coordinate system wherever you want. So in general case, it's not necessary, the mass matrix is not necessarily the diagonal representation. Okay, so anyway, so how about the details of my mass matrix? That will appear in a second. My computer needs some time to think about it, and now I figure it out. So it consists of 3 components, and these 3 components are associated to translational generalized coordinates, and that's this one. And then the second is the mass moment of inertia that is associated to rotational generalized coordinates, the angle theta. And then, this component that is located off diagonal locations, that's maybe non-zero, and it's non-zero if your body reference coordinate system is not located in the center of the mass. How is it you can make your diagonal representation of mass matrix? By putting your body reference coordinate system to where? The center of the mass. That's correct. All right? That's what I'm going to ask. I will ask that. Clear? Okay. Look what I'm doing here. Because I have a hidden agenda here. Maybe it's clear now that it's not that hidden agenda. But I'm really after that 100%. 100% success rate. And I'm somehow thinking that today is a day. That's what I'm thinking. All right. So now we're going to take a look at the quadratic velocity vector. I will explain it. And right after the explanation, I'm going to have an in-class quiz where I'm asking that thing, what's the consequence of putting my body reference coordinate system in the center of the mass? And that, by the way, will be asked also in midterm exam. So it's also something that is good to memorize. All right, so quadratic velocity vector. Let's look at the details then. All right, so this is what we just looked a few slides back. So again, my generalized inertia forces. Let me emphasize this. Generalized inertia forces because they are expressed in terms of generalized coordinates. They can be expressed such the way that I have the mass multiplied by acceleration of generalized coordinates and then quadratic velocity vector. Next, I'm going to take a look at the details of this particular component, and then I will give you a physical interpretation related to it. Okay? So how it goes then? So this is what I was actually expressed in a previous slide. So I have here my angular velocity, which is power 2, and then I have here my volume integral over the density of the body, and then I have my vector u bar component here, and my rotation matrix that is first differentiated with respect to angle theta, and then rotation matrix on its original form. This actually is simply because of the mathematics of when substituting that expression of acceleration and the mapping matrix, nothing else. Once doing the mathematics, this is how it actually appears. So this is how you can read it. And now this, in order to be able to understand what I'm about to say here next, you should actually take a look at a little bit about the nodes that are available in Moodle database. This part of the equation, the one that is inside of the circle, that is actually equal to 0, regardless what is the vector u bar, regardless of any other components. This is a mathematical proof that is actually explained in details in lecture notes. So take a look at that. So this part here will disappear from my final expression of quadratic velocity vector. So once I do all my integration, I can express my quadratic velocity vector as it is shown here. It is still quadratically related to velocity and angular velocity in particular. And then what I have here is my rotation matrix, and then something that is called here mass 0. And the mass 0 can be computed by taking the volume integral over the vector u bar and the density. So a little hard to see like how it actually goes. But again, here's my advice to you. So if you participate in the midterm exam, I think it is a good idea to practice this a couple times. You may need it if you want to score really high from the midterm exam. But if you're planning to score, say, 3 out of 5, then this is the one topic you can actually skip. And not just this topic, but there are other topics too that are less important. But what are these other topics? I will give that instructions to you on Monday. Next Monday, every single topics will be rated by stars. And if there's a lot of stars, it means if you're in a hurry, you can only invest, say, a few days to prepare yourself to written exam, study those subject matters, and leave rest with the little attention. That rating list will be available on Monday. Clear? Okay, now let's look what is a physical interpretation of this quadratic velocity vector. To understand that, I have here an example body. An example body is a beam-like body, like this thing here. Now, quadratic velocity vector is actually a vector that accounts the centrifugal forces on body coordinate system due to the rotation. And now, to understand that, let's look at this beam-like body and let's rotate that with respect to center of the mass, like exactly what I'm doing here. I'm rotating this with respect to center of the mass. And now most important observation is this. My body reference coordinate system in this particular case is located in the center of the mass. All right? And now my question is that how much center of the mass will experience centrifugal forces because of this rotation? How much that would be? Zero. That's zero. So he's not feeling anything at all. He's not feeling anything at all because it is in the center of the mass and I'm rotating this system with respect to center of the mass. How situation is different if I'm going to move my body reference coordinate system to this end and I'm going to rotate this as a pendulum like this. Is this coordinate system, is it experiencing forces because of this rotation? Yes. And it's actually quite a bit of forces, but because of, look at that, strong hand, no worries. So it stands still, so no motion whatsoever. But general case, there is a forces that are experienced the body reference coordinate system. This is exactly what the quadratic velocity vector is accounting. So it's a force vector. So it's a force vector that may or may not appear depending where you're putting your body reference coordinate system. Its amount, how much force is experiencing depends how far off is your body reference coordinate system from the center of the mass. Okay, so that's what it is. Now, like you can see, here are the two cases. In this case, body reference coordinate system is not able to recognize forces due to the rotation. Here, it is able to recognize the forces, and those forces will be the magnitude that is mentioned here. So, you see how it goes. So those are exactly the forces that the body reference coordinate system is experiencing due to the centrifugal force. All right, so that's what it is. You need some time to think? Maybe. We're going to practice that in a second. So not in a second, it takes a few minutes and then we're going to practice it. But are we good to go the first in-class quiz? Surprise? Oh, mass matrix of a body is a diagonal matrix F. And then the question mark. And now let me put my in-class quizzes on. So it's going to be this one. And then this one. And let me see that the room is correct. So room is a LUT room. So go ahead and log in and And I'm not sure how this appears in my streaming, but for online participants, maybe what I can do is to play safe, to make sure that the online participants can see the options as well. Mass matrix of the body is a diagonal matrix if, and here are my options. Body reference coordinate system is located in the center of the mass. Let me read it again. Body reference coordinate system is located in the center of the mass. Option number B is body reference coordinate system is located out of the center of the mass, but within the boundaries of the body. Body has a beam-like shape. Then the final option, body reference coordinate system is located outside of the body, outside of the boundaries of the body. 4 options, 1 is correct. And now if it is unclear, like if you're not sure what's the correct answer, come and discuss with me. I can go off from the camera so the online participant, they don't see you. Okay? So can I leave this? You need to have still some time to think, or this is absolutely clear for you? Absolutely clear. Very good. All right. So this is it. So now we have all the components that we need in order to build the equation of motion. Now the final thing I'm going to do here, just before I'm expressing the equation of motion, is that I'm assembling my bodies. I'm assembling my bodies to mass, or the system representation of mass and forces and constraints. Once I'm done with that, then that's it. Then I'm ready to express my equation of motion. Now, this is a mathematical explanation how it goes. Now I'm going to summarize the virtual work done by inertial forces from all the bodies, from body 1 to body NB. So there's NB number of bodies in my system, and mathematically you can express it as it is shown here. I'm going to do the same procedure to my externally applied forces, and then I can get all the energy in the system, all the virtual energy of the system, and those energies are associated to external applied forces again and inertial forces. Now, finally, because of all that, I can express my equation such the way that I have here my mass matrix multiplied by acceleration of tenorized coordinates. Then I have here my quadratic velocity vector, the one we just looked at, and then finally my externally applied forces. That's it. Now, what I have here, I'm shortly explaining how you do the assembly procedure. This is different than in the case of, say, finite-element method. I'm not sure if you're familiar with the method, but in a finite-element method, the elements that are essential components, they are constructed in such a way they are overlapping with each other. In multi-body dynamics, when we are building the system matrix for the mass and other components, they don't overlap. But instead, everything will be constructed. All the vectors, all the matrices will be constructed by using block diagonal representation. Block diagonal representation means that my first body is going to be located here. My second body will be located here, and they are not sharing any coordinates whatsoever. They don't share anything. It's just they are completely independent with each other. So first body, second body, and no overlapping like is the case in finite element method. Why is that? Well, that's simply because so why is that? That's simply because remember how I construct my vector of tenorized coordinates. How many tenorized coordinates one planar body needs? 3. How many tenorized coordinates 2 planar body needs? 6. How many coordinates 3 bodies needs? 10. 10. What? 9. Yes, right. Yeah, my mistake. So that's 9, not 10. So 9. So it always is multiplied by 3. The body number is multiplied by 3. So that's telling you that you keep on adding the vector of unknowns, and it's a function of the number of the bodies. So I'm not eliminating anything here, just keep on adding. Same procedure goes to quadratic velocity vector. For the first body, I will have 3 components for the quadratic velocity vector. And if I'm going to have a second body, I'm just adding those to my original vector with no thinking. Remember? No thinking. In multibody dynamics, no thinking whatsoever. Just do things mechanically. That's what's going to give you the equation of motion. So here's my second body, and then I'd go all the way to NB bodies. Externally applied forces, the ones that are associated with the first body, those will be 3 components. So they will be located here. Second body, 3 components, they will be located here, so on and so forth. So that's how it goes. Now, moment of truth. Is it going to be 100% or not? No. Yes. It's going to be 110%. No, 10% is enough. So 10%, and look at that. So we ready? So we have 87 students. You nervous? Yes, me too. So, so there's still some, you still need some time? Okay? Oh, look at that. So, can we round this up? Can we? It was so close, so close. So what happens? So now the numbers are changing here. This, in my mind, is equal than 100%. Good job. I'm quite happy about that. What bothers me a little bit is this 2% that goes incorrectly, but, you know, not significant. Not significant. Okay. Still going to make one more effort. And that the one more effort will be, by the way, next Monday, where I'm really, really hoping that it's going to be 100%. All right? Now, you got the assembly procedure and the constraints. That too will be assembled like it is shown here. So, no overlapping. So, this is the constraints that are associated with the first body, constraint associated with the second body, and so on, until you reach the NC number, which is my final constraint. Oh, excuse me. I want to correct that. So these are not, what I just explained, those are not associated with the body, but they have constraint ID number. Constraint ID number. So this is first constraint, second constraint, and then the final constraint. How you put it, that makes no difference. You can make them in any order you want. But once you make a decision regarding the order, then you have to be consistent. You cannot change that any longer. Okay, now, then comes a little bit surprising news. Because, you know, in the case of unconstrained system, the unconstrained multibody system, which by the way is not the multibody system, because remember the thing that makes system to be a multibody system. Constraints. So, but let's hypothetically look something that I have number of bodies, multibody, many bodies, but no constraints. How is that I can express my equation of motion in that particular case? Now you need to now focus here, because this has become to be essence of today's lecture. So unconstrained system, which is like potato-shaped body, potato-shaped body, and potato-shaped body. No constraints. They have no relation to each other. I need here 9 generalized coordinates to express this system, because I'm dealing with 3 bodies. How can I express the system, which consists of 3 bodies but no constraints? Well, I can simply say that virtual work done by inertial force is equal than the virtual work done by externally applied forces. Where that is coming from? Well, you know, it's coming from this equation that you're very much familiar with. That's it. That's the same thing. So it's a Newton's second law, which says that inertial force is equal than generalized the external applied forces. Now I'm just saying this in terms of generalized coordinates because it helps me to solve the responses. All right? So that's how I can express it. So this is that equality. So I have here inertia forces, which consist of mass multiplied by acceleration and then quadratic velocity vector, and then my external applied forces. This is how the equation of motion finally can be written. Now, this is again, let me emphasize, this is again in a case of unconstrained system. If I introduce a constraint to my system, then this equation is no longer equal to 0. And that's, by the way, this is may not concern you, but I'm sure that you have heard about this concept of virtual work many times before. And it's many times very much misused concept in the mechanics. And why it is misused? Because people always automatically, they set this equation to be this equation, they set that to be equal to 0. You cannot do that. You can only set this equation to be equal to 0 under the very severe condition. And this condition is very often overlooked. And that's why the concept is misused. What is this condition? Well, the condition is such that this virtual displacement, which is here, have to be kinematically admissible, kinematically possible. How it is expressed as the moment is not kinematically admissible. And why is that? Because I'm introducing the virtual displacement to all the generalized coordinates. I don't care about the constraints. It's just introducing the virtual displacement to random way, and it can violate and it will violate against the constraint. And that's why this equation cannot, in general case, set to be equal to 0. All right. Now, again, this equation cannot be set to be equal to 0 because what I'm not accounting here is constraints. And the constraints makes it such that this, the way this virtual displacement is expressed at the moment is violating against the constraint. So that's why, in general case, I cannot set this to be equal to 0. You got it? Clear? Yes. Okay. Equation cannot be set to equal to 0 because inertial forces are not accounted. External applied forces are not accounted. Constraints are not accounted. No forces are accounted. Hold on. Would you like me to go back and repeat what I just said? Yes. But you said that it's clear before. No, it wasn't you. It was someone else. Let's go back. Let's look at this situation. Don't answer. Okay? Now, this equation, you cannot set this to be equal to 0 because the virtual displacement, it is introduced to all the generalized coordinates. All the generalized coordinates. So let's, hypothetically, I don't know if this is clear drawing, but let me see if my pen is now cooperating. Yeah, it is cooperating. But I kind of think that my finger is making better drawings than my pen. Kind of. Okay, so I have here a pendulum body, just the one pendulum body. And this pendulum body has a body this is okay, it's a body coordinate system that is located here in the center, roughly center of the body. And this system has a generalized coordinates that are Rx, Ry, and angle theta. All right. Now, the way my virtual displacement is introduced here is that I'm introducing my virtual displacement to all these generalized coordinates. Let's give a first the Rx. It means, let me change the color here, this one, that the body will move this configuration. Just a little bit this configuration. So what is the consequence of that? My constraint is no longer fulfilled. That's why you cannot set this equation to be equal to 0, because the constraints are not accounted. The constraints are still missing. They are not accounted. All the forces are there, but the constraints are not there. Clear? Okay, so it's all clear. All right, so then let's look at this. Next. Somehow I'm kind of feeling that I'm feeling very strong today. So kind of thinking that we're going to score very high again. Very high is more than 70%. More than 70. Okay? Now, think about this. And I will get back to that in a second. Now, excuse me. Now let's look at the ways that we can actually express the equation of motion such that the constraints are accounted, that they are accounted. Roughly speaking, we have two choices, like is in a case of optimization when you have a constraints, that you have to fulfill the constraints. If you look at your mathematics back when you were, bachelor level student, I'm sure you learned two different ways to do the optimization, the constraint optimization. And there are two ways to do it. Let's first look at the most obvious way. Now this is pure mathematics, nothing to do with the multi-body dynamics yet. But soon everything comes in a framework of multi-body system dynamics. So I have a question here that I would like to minimize the equation, which is written here. So minimize this equation such the way that I am fulfilling the constraint. And my constraint is this one here. My function is 1 divided by 2, and then that multiplied by y1 power 2, y2 power 2. That's my original function, and this is my constraint. And I need to minimize this function such the way that I'm not violating against the constraint. How can I make it happen? By substituting. Correct. So what I can do is that I can solve, say, y1 from this equation by putting everything else in the right-hand side of the equation, and then take the y1, substitute it here. What is left is only y2. And how can I find an optimal point? By differentiating that with respect to that variable. That's it. So that's the one way that I can make this happen. Oh, now, by the way, how is my streaming? Is it still all right? Because I can see that this moved a little bit to left. Is it still all right? It's all right. Okay. Now, so let's look at this first option, which is this obvious option. Okay, so I just did what I explained. So this is my original function. This is my constraint. So I first solved the y1 from this equation, and then I substituted that to my original equation. This is how it reads now. So this is how finally it appears. And now when I differentiate that with respect to my variable y2, I get this equation. And this becomes 0 when y2 is equal than minus 1 divided by 2. Now in the similar way, I can solve this other variable, like, well, I don't have it, I'm obviously missing one slide here, but I will show it to you a bit later. But that is when I'm substituting my constraint to my original function. Have you ever heard this other technique that is based on adding my constraint to my original function with help of Lagrange multipliers? Yeah, that's what I was thinking, because they teach that already in high school, junior high school, elementary school. No, before you learn to read. Well, they have you ever heard it? But you can do this to show off to your fellow students. Yes, I'm familiar with the concept. I learned it already a while ago, so it's all clear. Well, let's look at what I'm doing now. I know that is exactly time to have a break, I don't care about that, because let me first explain this, and then I'm going to explain it again after the break. All right? So I'm going to look at the theory of optimization, constraint optimization, and then I'm going to redo this very same mathematical example that has not yet anything whatsoever to do with the multi-body dynamics. Okay? So how it goes? It goes this way, mathematically. If you wanted to find an extreme of the function, this one here, that is subjected to constraint. Constraint is this one. Now I have variables x and y. They could be something else too. So it's, don't get confused about the mathematical details. But again, I have function, this one, and constraint. I wanted to find an extreme of my functions. That's the way that I'm not violent against the constraint. How can I make it happen? Well, based on the constraint optimization, I can compute the gradient of these two functions, original and constraint. Now once they are parallel, that's where the extreme is located at. So I'm computing the gradients of both original function and my constraints. Once these gradients are becoming parallel, that's my point. That's where the extreme is located at. Do you hear me like extreme parallel like that? Fine, completely fine. If you don't understand the mathematical foundation, relax. Take it easy. It's still gonna be fine, because we assume we're gonna look this in a more concrete way. So even if you don't understand that, your life is gonna be fine. All right? And if you understand it, that's even better. All right? Now, these gradients generally have a different length. So in order to find this extreme location, we find that they are parallel, but they may have a different length. So we have to multiply one of these gradients with the number that is unknown, and that number will be called Lagrange multiplier, to make them having exactly same length. And that's how can I carry out my optimization problem. And the one that is making the length of these gradients to be same, oh my God, it's very unclear writing. How can I take this off? Yeah. Are they removing? Yes. So this is the one that is making these gradients to having the same length. This is my gradient associated to my original function. This is my gradient associated to constraint. And the lambda make them to have the same length. All right? Okay, let's look at that in the previous example. So I have here my original function. I have here my constraint. And this is exactly same numbers. I think they are exactly same numbers. I think they are. All right? Now, let's first compute the gradient of my original function with respect to variables. And I have here two variables, y1 and y2. So this is my original function. And when I do the same to my constraint, this is again my constraint. It goes here. This is my gradient. So these are the two gradients. So when they are parallel, that's where the extreme is located at. But still I need to use these Lagrange multipliers, to ensure that they have the same length. So this is my gradient, and I'm multiplying this one with my lambda. So look at how it goes. This goes here, this goes here. And then I'm still accounting my constraint. So I'm taking one more information into account, and that is my original constraint function that is shown here. That's the way that I can solve the exactly same problem that I did with my substitution technique. But this time, I'm adding my constraint to my original function with help of Lagrange multiplier. One multiplier because of the one constraint. Now I have three unknowns. And these unknowns are y1, y2, and Lagrange multiplier. By the way, Lagrange multiplier by the definition means price you have to pay because of the constraint. Okay, very unclear. Price you have to pay because of the constraint. What is that? What's that for us? For us, that's the clear thing. There's a very clear physical interpretation, and that will be reaction forces due to the constraints. Reaction forces due to the constraints. Okay, so now we have 3 equations, 3 unknowns. I can solve this whole thing. That's it. I can solve this this problem in a I can get the same solution than in a case of substitution technique, but I also get this one additional variable, which is the price that I'm paying because of the constraint, reaction forces. Confusing? So I figured this out already a while ago, right? You still know how to find it out from the lecture room? Without my help?
What is lambda?
Lagrange multiplier. Price you have to pay because of the constraint. Reaction forces in multibody dynamics. Okay? I think you need a break. Do you? Yes, you do. Let's have a break. Yes. Okay. So, what's this? What's going to be the success rate here? 71. 71. It's going to be, no, it's 70 because this is still very unclear because we were looking at the virtual displacement of generalized coordinates, and then I'm asking what is missing there. I said it, but still, because you don't listen to me. So that's why it's not going to be that simple. Okay, still is a more coming. Okay, so now I'm going to close this. Oh, very good, very good. 97, 97. Good. So definitely, they're still coming down. Those are not accounted. Those are not, we scored 97, period. Okay, now let me close the recording. What?
4, 2 plus 2 plus 1 plus 94 is 99.
Yeah, it's I don't know. I don't do this software, so I have no clue. Okay, let's have a break. Then I will explain it again. Then we're going to look at the Lagrange multiplier in a framework of multi-body system dynamics. And then that's it. That's it. Then we're able to express the equation of motion. Okay, let me close recording. Where is this? Here.